Okay, hey guys, I just want to go through your Unit 2 review, Matter and Chemical Change. Just make sure that you got the right kind of ideas about these things. So, number one says explain the difference between atoms, elements, and molecules. So, an atom is kind of like we had the atom builder game that's on Mind Shukin's website there, where like an atom, let's say an atom of hydrogen, which is easy, would have just one proton in the middle and then have an electron orbiting around the outside, right? So that's a hydrogen atom. An element, the only real difference is that elements are made up of a bunch of atoms. So hydrogen, the element of hydrogen would be made up of a whole bunch of hydrogen atoms. And then lastly, molecules are things that are made up of more than one type of atom. So for example, water, right? H2O. So you'd have one hydrogen atom and it'd be bonded with two oxygen atoms. There's my baby crying in the background. Okay, so hopefully that's clear. Number two here says summarize the 5 main points of the particle model of matter. So I'm just gonna go here quickly. So it says so the particle model of matter. All matter is made up of extremely tiny particles. That makes sense, right? Like they're very, very small. There's literally trillions of atoms in just your finger. It's mind blowing how small these really are, right? Um, Second one, each pure substance has its own kind of particle. So that's almost a given too, right? Like gold is its own type of particle. It seems pretty obvious to us now, but it wasn't so obvious back then when this was first proposed. Particles attract each other. Particles are always moving, and particles at higher temperature move faster on average than particles at lower temperature. So, and that's, if you remember, since we're on the same page, remember gas, liquid, and solid. Particles are moving faster in a gas, right? They're actually able to escape their bonds. They have a higher kinetic energy too. All right, so number 3, how do particles of a solid differ from particles of a gas in terms of, so let's just draw a picture maybe of like that standard picture you've seen of a solid, bunch of stuff all in the bottom of the glass, and then of a gas where they're all kind of spaced apart, right? So how do particles of a solid differ from particles of gas in terms of amount of energy? Well, this is our gas, right? This is our solid. The particles of gas, the whole reason why they're able to be so separated is because they have more energy. They're moving faster. So in terms of amount of energy, the gases have more energy. The amount of space between one another, well, again, these have more space between them, right? Amount of movement, the gas is definitely moving more. So the solid, I guess in terms of the solid, they're not moving as much, right? All right, moving on to the next one. So number 4, what is the difference between a mixture and a pure substance? So a mixture contains 2 or more different things, I guess you could say. So a mixture would contain, let's say, if I had a mixture of water and iced tea mix. That's 2 different things. It's a mixture that we've made. A pure substance would be something like water, right? Water is, and this is where people get confused too. Water is H2O. So then people might automatically be like, haha, there's 2 different things. It must be a mixture. But it's not. We consider a molecule one thing. So water is made entirely up of H2O. So we call it a pure substance. A mixture, on the other hand, would be made of more than one thing. So common examples are like gravel or sugar and water. A pure substance would be H2O or just sugar or, yeah, lots. So moving on to number 5. Is a pure substance the same thing as a pure element? A pure substance is not the same thing as a pure element. A pure element is a type of pure substance. So a pure substance, like I was saying to my class today, could be something like H2O, right? A pure substance, we'd say H2O is my pure substance. A pure element, on the other hand, would be made up of something entirely of the same element on the periodic table. So gold. Yeah. What is the difference between a homogeneous mixture solution and a heterogeneous mixture, more mechanical mixture? All right, so I drew a couple pictures. Homogeneous solution is going to be something that deals with something that is all pretty much the exact same. So it's going to look like one kind of blended thing. It's all going to look like the same substance. A heterogeneous solution is going to look like there's definite little bits that we can see. It's made up of different things, right? So yeah, and that's what we call like mechanical mixture. So I don't know, you think of like gravel or granola bar or something like that would be a common heterogeneous solution. Homogeneous solution might be milk, something that looks like it's one thing, right? Or maybe iced tea or something like that where you couldn't see any of the particles moving in it. All right. So distilled water. A couple people were confused about what the word distilled means. Distilled just pretty much means it's pure. So pure water. So that's going to be a pure substance. It's pure water. It's pure substance. Granite. And if you can't think of what granite looks like, just to make sure the picture helps. This is granite, right? Different pictures of granite. You can see the different parts of it. Granite's made up of a few different types.
Starbucks just announced its new Frappuccino.
I had an ad going. Made up a few different types of rocks, right? So this is what we call a mechanical mixture. So mechanical mixture for B, apple juice would be a solution. Okay, so for number 8, it says complete the following chart comparing physical and chemical change. Yeah, okay, so the first one says what changes, and I drew a picture of a tree because this is a kind of a common physical change, right? And what changes is actually just the arrangement of the atoms within the substance. So in this case, this tree was standing up, right? It was all one type of, or it wasn't all one type of atom, but it hasn't made a new substance, right? All that happened was all those atoms have just changed place. So cutting down a tree, they're still the same atoms that they're originally making up the tree. There's no new thing that's making up this tree, right? It's just in two different places now. Another example would be heating like water up or to steam or freezing it into ice. You're just changing the arrangement of those atoms, just the way they are, but they're still the same atoms. For chemical change, on the other hand, what changes? We actually have a new substance that comes out of it. So if you look at this reaction, right, I've got CH4 and O2, so it's a combustion reaction. We've got two brand new things that come out of it. We've got water and carbon dioxide. These two things have changed into these two things. So chemical change is the really big thing to know here is that we get new substances coming out of it. That's the main thing about chemical change. So then I've kind of answered the question for the next ones too. Is a new substance formed? No. Yes. Is it reversible? I found that there's been some confusion about this question. We probably shouldn't have even asked it, because if you think about a chemical reaction, I've said something like, cooking a steak. Cooking a steak would be a chemical change, right? Because you get a new new like charred part of the steak, and you can't uncook a steak. So it's kind of a common thing to say to know that you had a chemical change. But people in my class keep looking at like the picture of the tree being cut down, and they're like, but I can't reverse that tree being cut down, right? So it's probably a bad example. I'd say the better way to think about physical and chemical change, like I said before, is to think about, do you get a new substance out of it? If you do, it's a chemical change. If you just have the same substance, but it's just been rearranged, whether it's a gas now, or now it's a solid, or now it's just in two places instead of one, like our tree example, then it's a physical change. So you guys can come up with your own examples there. But yeah, so sorry about the is it reversible question. Moving on. So number 9 says list 6 pieces of evidence scientists use to determine whether a chemical reaction has taken place. So right here in your textbook too, and it even says in your textbook too, probably. You can see the word probably taking place here. It's because it's not a cut and dry thing. So here's actually more than 6. So heat is produced or absorbed. That might be a good indication that there's chemical change. The starting material is used up. There is a change in color. A material with new properties forms. Gas bubbles form in a liquid. A precipitate forms in a liquid. And people kind of forget what precipitate means. It just means like the little powder. So let's say you like mix 2 liquids together and you end up getting like a powder that comes out of it. That's like on the edge of the glass. That would be called a precipitate. So forms in a liquid. The change is difficult to reverse. So that's kind of what we talked about before, but it can be reversed, or in some instances it can be reversed if it's a chemical change. So again, probably. All right, going on back. For number 10, says determine whether each of the following describes a physical or a chemical property. I just want to go over something kind of quick. Oh, wrong one. Okay. So you guys have this table in your textbook too. So we got chemical properties and physical properties. It's on page 104 if you're interested. So chemical properties are really talking about whether it's something that could change the chemical or the chemistry of the object. So does it react with something is pretty much, I guess, what we're saying for chemical properties. Physical properties doesn't really change how it's going to react with anything. So you can see we've got like reacts with water, reacts with air. If you see the word reacts, you're dealing with a chemical property. So kind of a dead giveaway. Reacts with acids, other pure substances. Toxicity. So toxicity, it's also kind of saying it's going to react with your skin or with you, right? And combustibility. Is it going to react by igniting? Physical properties. We've got color, melting point, all these type of things. But you see we've got qualitative and quantitative. So qualitative, you can think of like quality is the only way we can kind of talk about it. Quantitative usually means we have like a number we can assign to it. So quantitative, I can actually say the melting point for water is 0, right? I can give it a number. Same with all these things. You can assign a number to every one of these things. Qualitative, when we can only talk about the quality really of what we're looking at, you can't really say it has a texture of 2, like it has a taste of 3. So that's kind of a simplistic definition between the two of those. So, but these are different types of physical properties. So if we go back and look at these, so reacts with oxygen. As soon as you see the word reacts, you know it's going to be a chemical reaction. Highly malleable. So malleable, when I think of malleable, if you forget, I think of like blacksmith being able to mold or like hammer metal into the shape of like a sword or like a horseshoe or something like that. It means the metal's malleable, which is a physical characteristic. It's just being reshaped. Not soluble in water. That's physical. Maybe I'll put a P, C. pH of 4. Funny enough, online there's actually a bit of like controversy about what pH would be, but pH affects how it would react with a different substance. So if it has a higher pH, it's probably going to react more vigorously with it. So pH of 4, we'd say it's a chemical. Conducts electricity, physical. Yellow in color, that's just the way it looks, physical. Extremely toxic. Toxic is how it reacts with us, or living creatures. So that's going to be chemical. And low density, that just means that like the object's been like it's packed, I guess you could say. So physical. All right, how does a law differ from a theory? And almost everybody, adults included, will probably say something like a law is something that has been proven, and a theory is just somebody's idea. Like that's just something that they got a hunch about maybe. And it's kind of almost the opposite of that. A law is something that happens every time. So let's say if I drop something like a rock, a law might be that every time I drop this rock, it's going to fall to the ground at an acceleration, a certain acceleration. I won't get into that. Where a theory is more powerful than that. The theory will explain why that rock falls to the ground. It'll say that, well, the Earth is way bigger than the rock, and according to Einstein said that really heavy things warp space, so that ends up making smaller things kind of fall into them. So that'd be the theory of gravity, which is a lot more powerful. It explains a lot more. So theories, I guess you could say, are better than laws, which is kind of the opposite of what people think. And you know what? This video is getting kind of long, so I'm going to make a new video, and I'll stop this one here. So see you in the next video.